Welcome to LIB Academy. In this video, we are going to look at the total energy of a system, which is the Hamiltonian operator. In classical physics, the Hamiltonian operator, which is the total energy of a system, E equal the sum of the kinetic energy and then potential energy. And we know a relation, for now, let's replace kinetic energy by EK, potential energy by EP. So the total mechanical energy in the classical world equal the kinetic energy, which is half mv squared plus the potential energy. So we are trying to move from classical physics to quantum physics, right? And when we are moving, this is a Hamiltonian in classical physics, and we are trying to go to to work around it so that it will lead us to the quantum world. We are trying to manipulate it so that we'll be able to describe quantum systems, right? Okay. So in this case, we know momentum. Let's say momentum P let's say px in the x direction to be the product of mass and velocity, right? So let's try making v the subject. We are going to get px over m. We want to replace this v squared here by a term that will contain momentum, linear momentum. So now we want v squared. Let's square both sides. Squaring both sides will give us this. So we are going to replace v squared by px squared over m squared. So here we get our total energy to be half m then px squared over m squared plus our potential energy term. So in this case, m here we take care of one of the m here, so we can get our energy term to be equal to 1 by px squared, which is px squared over 2 by one of the m here, which is the same as 2m plus ep xt. So now this is a classical Hamiltonian, right? So we want to manipulate this into the quantum Hamiltonian. So what we do is that we replace this momentum here by the momentum operator. In our previous video, we learned how to derive this momentum operator. And we are just going to state it here. It is something that we need to know off head because we will be needing it. So our linear momentum operator equal h over 2 pi I dx. We got this when we divide the wave function. When we take the derivative of the wave function with respect to x. That is where we got this. You can check that video out or try to find some understanding on it. But for now, you have to know it off it. So we are going to replace the momentum term by this. But you will see that the momentum term here is squared. So there is a need for us to square this whole thing here. So there is a need for us to square this whole thing here. So we are going to get px squared is going to be, we square h, like we definitely square everything. Let me write it this way in order not to confuse myself and you. 2 pi I d over dx all squared. So if we expand it, the square will affect h here. It will affect 2. 2 squared gives us 4. Pi square I squared. Okay, let me write just I squared. We will look at it later. And then d squared over dx squared. So we can now go ahead and replace this px squared, the momentum term here, by the momentum operator, the square of the momentum operator, right? Okay. So we are going to get Now, in the quantum realm, our Hamiltonian, we are not going to call it E, we are going to call it H hat, right? This is what represents our Hamiltonian operator. So now our H hat equal, we replace a square, this, and we are going to have H squared over 4 pi squared I squared, and then D squared over dx squared, all divided by, okay, let me bring it here, divided by 2m, then plus the potential energy EP x t. So now let's move it forward. Let's move forward. Now what we do is we want to multiply this by that, so we just take the reciprocal of it. Okay, so we have h squared all over 4 pi squared I squared d squared over dx squared multiplied by 1 over 2m plus our potential energy. So now let's try to expand everything here or simplify everything here. So 2m will be multiplying the whole of this, so we can represent a Hamiltonian operator. Hamiltonian operator to be equal to h squared. So 2 by 4 gives us 8. We have pi squared, and we have I squared, and we have d squared over dx squared, right, multiplying 1. So plus our potential energy term. So here we know that I equal root of -1, right? So if we squared, so I squared is the same as root of -1 all squared. And this square term is going to take care of the square, leaving us -1. So the whole of this term here can turn to -1. So we have h squared over 8 pi squared multiplying by -1 d squared over dx squared plus EP x t. So now everything with -1, this term is just the same as writing minus h squared over 8 pi squared. Don't forget that our m here, we didn't bring our m here, right? We should have m term here. Sorry. Yeah, m term here. So 8 pi squared m d squared over dx squared plus our potential energy term. So this is now a Hamiltonian operator. This is a Hamiltonian operator. Once you know that the total energy of a system equals the sum of the kinetic energy and the potential energy, you now introduce the relation between momentum, the relation of momentum, which is called mass, mass times velocity. You find make v the subject, square it, replace v square by the product, then you get a term containing momentum. Then you now replace the square of the linear momentum operator. This is a linear momentum operator. You square it and place it over there and simplify your expression to get the Hamiltonian operator, which is this. That is it for this video. Thanks for watching. See you in my next video. If you found this video helpful, kindly subscribe to my channel and give a thumbs up to this video for more educational content like this. You can also refer my channel to your friends. Thank you. Bye.